Yeah, thank you very much. So I think most of you already know about what is Coulomb branches, and I will introduce some variant of Coulomb branch construction, which is called SVR varieties, originally introduced by Kavli in 2008 in the context of their approach to the Langland singularization in terms of the gauge. And the Coulomb branch and SVR varieties are basically just variant. So once you understand the Coulomb branch, you can understand SVR varieties, and vice versa. Once you understand SVR varieties, you can understand Coulomb branches. But one of the advantages of SVR variety is if you want to understand the hyperkähler quotient, the symplectic reduction of the Coulomb branch, I think it is better to go to SVR variety. So in this sense, this talk will be a combination of arguments. Okay, let us first talk about the easy case of abelian group acting or maybe torus acting on Coulomb branch. Maybe I cannot Coulomb branch MC. So MC was constructed as some homology group of modular space defined on this cartoon for algebra model of the two sphere. So the union of two disks glued along punctual disk. And in particular, so modular space has many connected components. So this is in fact parameterized by fundamental group of G. So basically, for example, if G is a general linear group, this is just the degree of the band. So then the homology group of some space is decomposed into direct sum according to connected component. So this spectrum. So the function coordinate ring of the Coulomb branch is graded by is graded by pi1 T. So MC has action of the Contriagin dual of G. Dual. So namely, so for example, G is GLN, then pi1 of G is D, and its Contriagin dual is C star. So if you have the C star action on the Coulomb branch, then its coordinate ring has weight space decomposition, and weights are integers, and this coordinate ring is graded by integers. So in general, if you use the Angerson Contriagin dual, and this Contriagin dual is always abelian group, and if G is called GLN, then this is. And in this case, you for example, if G is GLN, so I have an action of C star. And in this case, one can show that MC, quotient of MC, symplectic reduction of C by C star is another Coulomb branch. But you replace PLN by SMS. So this is a very general statement. Starting from our definition of the Coulomb branch, it's not so difficult to check this. So in that sense, the reduction of the Coulomb branch with respect to this kind of torus action is easy. And also, maybe more related example is toric hyperkähler manifold. So if you have the exact sequence like this, and I denote the quotient by TF, so this is the flavor symmetry group, and you have the action of M, energy measure, extra space, dual space, then the Coulomb branch. So Higgs branch of this T and M is a symplectic reduction. which Namikawa-san used to consider some examples. And the Coulomb branch in this case is M, the same M, but you have the dual exact sequence. You use the dual exact sequence. And TF check, and T check, and you take the quotient by TF check. So you exchange T and TF check for Higgs and Coulomb branches. And this can be this can be understood in this way. MC of T of M is MC of C star of N so you take, so this is a variant of this construction. So you consider larger Coulomb branch for larger group, and then take the reduction by. This is a general result again. Yeah. And you just compute in this case. You just compute this is M itself. So in this way,
you have cases where it's a scale group instead of a continuous group?
So this construction is general, and so for discrete group, you just the symplectic reduction is just a quotient. Okay, but I'm interested in non-Rak-Kyeong. So then I have example where the Coulomb branch is related to the symplectic reduction. So this is a case of quiver gauge type affine type A. So in this case, I explained the construction in the last week. So you can realize this in terms of D-plane, the length, and the planes. And then in order to compute Higgs and Coulomb simultaneously, you play with D-planes and E-planes. And it can be rephrased as follows in mathematical reduction. So suppose you have, let me see what. So this is maybe just detail is not important. So MC of Coulomb branch of this kind of theory is symplectic reduction of product of the following building block by diagonal. So I draw this kind of diagram. So this describes the Coulomb branch, and I decompose into the building block like this. And each segment is assigned integers. So for example, maybe this is 0. I assume that the leftmost and rightmost intervals are assigned 0. Like this. And then if you have V and V prime, so this is a building block. So then I interpret this as homomorphism C of V, C of V prime, with the action of GFV times GLV prime. Another building block, V and V prime. So this is the cotangents. This is a symplectic manifold with GLV, Hamiltonian GLV times GLV prime. So this has 3 cases. So if V is equal to V prime, so this is T star of GLV times C of V. And you have, so again, this has action of GLV times GLV. So in this case, basically this is a left and right multiplication, and CCV is this is only left multiplication. And next one, if V is larger than V prime, it is GLV times S of V minus V prime, 1 V prime. So here S of rho is Rho-Lewis rise to nilpotent orbit. So this is I consider in the real algebra. So this is some vector space. And so this is a partition. So I'm considering the nilpotent orbit in GLV, so it corresponds to partition. And so partition is of this type, hook type. So you have V minus V prime, and you have V prime. So my convention is nilpotent element. So this is this nilpotent endomorphism will go in this way. So you have big nilpotent block, a big principal block, and then extend by them. Then you have an action of the So GLB acts by multiplication, and GLB prime acts on this block. And if B is smaller than B prime, then just exchange V and V. Or, so this is also in the differential geometric language. This is a modular space of solutions of terms equation. This ordered middle. And you must, so terms equation is the ordinary differential equation whose value is matrices of size B and B prime, and this has singularities, and you must assign some specific boundary behavior at this point, singular behavior at point, and this behavior is fixed by this choice of nilpotent. So anyway, so this is some detail, but you have some concrete variety with an action GLB equal to GLB prime.
So the first element, the first line of the vector.
This is just a vector space, so it's also the building block for the quiver variety. So in the quiver variety case, so we put, in that case, we put all circles. Then we just use this vector spaces and take a product.
So
this one,
kind of,
well, but this is just pairs of linear maps, and it's difficult.
So circle is a dimensional 5 circle is dimensional 5.
Circle is NS5, and this is D5, and this D means that D copies of. So if you, in the notation Nami has lecture will be on Friday. So anyway, as I said, so Nami has analysis of the Coulomb branch and Higgs branch by realizing gauge theory in terms of the branes, and this is just my way of drawing the branes, and from this you can write down the corresponding Higgs and Coulomb branches, and Coulomb branches is you assign this vector space like this and take a Hamilton by the GLB and GLB and so on. And for Higgs branch, you just replace circles and curves. So this is one good examples of where we can understand both Higgs and Coulomb branch completely. So in particular, we proved this by, I proved this by with my former student Takayama, and somehow the argument, of course, we cannot use deep branes, it's not mathematically rigorous, but somehow we have some recipe to, once we have some candidate of the Coulomb branch, and then check several properties of those candidates, and then we can conclude that it's Coulomb branch. So this is anyway. So this is not illuminating eliminating proof, but somehow I think not that I try to explain why this is compatible with SQL. I think that it's more relevant in those SQL. Any question? So I first recall the notion of balanced vertex. So which I think I have already explained in the talk. So we consider, from now we consider equivariation. So we have Vj and I. Okay. This might have framing. So this circle is framing and circle square is framing. This could be called. Framed equirepresentation. Then we say I is balanced. It's a combinatorial condition. So 2 times Vi is equal to I Vj plus J plus WI. So if this condition is satisfied, we say this is balanced. And we have this the following theorem. So suppose we are given a equivariation and the mark all balanced. Vertices. So I marked, I balanced. So I set of vertices. Then, so I balanced, I mean, except something is affine case. So this is the union of finite AD type thinking diagram. So because of this condition, I mean, even if you start with the arbitrary affine thinking diagram or more complicated thinking diagram, if you just satisfy considering vertices which satisfy this condition, you can show that this is finite union of type AD thinking diagram. So then I have corresponding group of simply connected type. So maybe this G should be different from this G corresponding group. Then our claim is MC has an action of G. So this no-abelian group acts on the Coulomb. I mean, of course, this was known in higher maybe in the physics lecture, but somehow we check this property in our definition, mathematical reverse. This is first statement.
G is the symmetry of some.
Symmetry. G is the group, simply connected group corresponding to this thinking diagram. This axiom. G is nothing to do with the original gauge group. Original gauge group is a product of general linear.
So the full one has symmetry.
Yeah, we don't say that this is a full symmetry, but we just say that this is at least this group action.
So here you always have simple group.
Product of. This could be products. Any quiver, anyway, I suppose. So if you have something like this, then with just some all the nearby variables. And the second statement is we proved in the context of the classes, each branch of classes, that this is more general. So suppose we have n and n minus 1 and so on, up to 1. And n is connected to the other part, and this part I don't care. And then suppose I also have similar thing. By the way, I should also say this extends to. So you have T, maybe sister of. So for the quiver case, the each vertex, we take the general linear group. So its fundamental group is Z for each vertices, and I have the corresponding torus actor. So I have yes, this is not strictly contained, but somehow, if so, you must slightly enlarge this group G rather than this linking diagram, because if G is SLN, then I want to replace it by GLN. So this is a little bit not quite correct, but I hope this is minor difference. So you could have it. Then I take the pairs of Coulomb branch. So this part and this part could be completely different. And then I take the symplectic reduction by the diagonal GNN. So this part is this part and this part up to n minus, and this is balanced. This is balanced. So you have by this rule you have SLN action, but in fact in this case you have the action GLN because you also have extra system. So then the statement is, so you can consider these are two legs in this diagram, and then you can glue you can somehow eliminate the legs simultaneously. So this is MCO. Maybe the number of legs should be different. And you have this one. Right? So it's a big branch of classes. So this is considered by Mura and Tachikawa. And they propose several expected property of the Higgs branch of class S theories. And this is mirror class S. So this gluing property is one of the properties. We gave a mathematical rigorous proof. And again, this proof is not illuminating at all, and we use some very deep result in derived geometric Satake. And once you use this language, then somehow not so difficult. But not so difficult. Any question? I think this is GLN. Always, if I mark by circle, then it is always, it's not, I don't divide by the overall system. So this just gives the extra sequence system. So then, if you want to make to reduce by overall C star, then this should be SN. But in my convention, this is also gauge to know. Okay, then, for example, so by corollary, so we consider the Quiver gauge theory like this. So we have somewhere in the middle, we have this part, and it continue to left and right. Then, so V and V minus 1. Okay. I switched to. So this part is a bit I changed. Right. So this certainly compatible with my description of the Coulomb branch for Quiver gauge. So if you have this part, then this. So more generally, so. So for example, you can compute this one. So building block. So this is, so if you consider the following, the Coulomb branch of so this is balanced. This is balanced. So you have an action of GLB, an action of GLB prime. So this is, and this part is what we wrote in this way for the border. So this is isomer. So using this and this successfully, so we arrive at this proof of the computation of the Coulomb branch for the equivalent ASL type. So let me give now I give the definition of SDR variety. So it's originally come from the SDRT for the four-dimensional theory, and we regard the three-dimensional theory as boundary condition. So suppose we have G and M, and in fact for this, and I assume this to be T star N. So for the gauge array, I assume M to be representation, but in this formulation, I think that it is not necessary to assume. This is a Hamiltonian G space. So you have the M is a symplectic manifold, and N is a usual manifold, and G acts on M by preserving symplectic form, and you have the more corresponding momentum. After this is the definition of Hamiltonian G space.
So when you link back circle to weighting, those vortex, this curve back.
Yeah, this is bad quiver, but our definition doesn't distinguish that. Yeah, so this makes sense. And also this result, so for example, GLV times S of V minus V prime, 1 of V prime. So this is not the conical. You have the C star, but this is not the conical. So in that, so for our cell construction, the bad and good and ugly is just the difference of the C star action. So if this is C star action is conical, then it is good to say good to ugly. But our definition doesn't distinguish. So yeah. So we define the dual variety by this formula. So I need to explain what is TG. But basically to say like in here, so I want to have this example. Example, if M is T star of C of V and C of V prime, this GLV. So this is G, and this is my M. So this is a special example. Then I want to define M check to be this one. And in general, so you have so this, I talked about only type A, so you cannot distinguish it. Or I just to talk about general linear groups, so I cannot distinguish the group, the original group and the Lagrange dual group. But in general formulation, you should replace this group by Lagrange dual group. So in particular, this M check is, this is Hamiltonian. G check space. So what is TG? So in this TG, in this case TG, so this is and you have the action. And you take the Hamiltonian reduction for those n minus 1 vertices. So in our definition of the Coulomb branch, we usually assume that M is a smooth space, so it doesn't directly apply to this. We cannot put T of G in here, but we interpret. M かける this space. So you change all the circles to boxes. But you also take the Coulomb branch with respect to those groups. Okay, then once you understand in this way, then the gluing theorem, it's like, so this is the concept of gluing theorem. So if you have M1 and M2, so G Hamiltonian space, then the Coulomb branch of G of M1 plus M2. If you first compute this M check, M1 check, and then M2 check. I must. And also, so one of the main conjecture so if you take the SDR twice, then this is isomorphic to the origin. So you have Hamiltonian G space and you have Hamiltonian G check space, and you apply the same constructions. Then you recover the origin. So this is useful. And for example, from this example, so this is not a vector space. So you must somehow generalize the definition of Coulomb branch so that it can be applied to this case. But then once you expect the definition can be generalized to this case, so our definition makes sense if M is cotangent bundle to some space. But this is not cotangent, so you must generalize the definition. But once anyway, so this definition can be generalized, then M check by this conjecture, M check of check recovers this space. So this is expectation. Yeah, I try to explain how the subtraction I explain can be derived from this. First, thank you.